All right. Hey, everybody. Thanks for those that have joined already. Sure, we'll have some more trickling in, but we'll just go ahead and get started. All right. So I want to thank everybody for joining today. Today we're going to be talking about AC and DC coupling and kind of how it relates to the SimpliPhi battery, but also in kind of more of a general sense too. And we're also going to be diving through a little bit of what SimpliPhi has to offer for AC and DC coupling. A few housekeeping items, questions during the webinar. There is a Q&A section at the top. Go up to that black bar, hit Q&A, type in any questions you have as you go through. And I have a little time carved out at the end. We can go through some questions. All right, a few other items. Check out our training calendar. It's pretty packed right now. We got a lot of trainings coming up here. So if you're interested in any other trainings that I might be doing, or also some of our new trainers, check it out. We got a lot more to register for right now, and even have some cool ones coming up this week. Next week, we're going to have a webinar on all of our different web tools. That one should be a really fun one, and tons of other stuff coming up. So check out the calendar if you have anything that you're interested in signing up for. All right, with that, let's hop right in. So here at SimpliPhi Power, the kind of proven or motto, I guess I kind of try to stick with: safe, proven, and simple technology. So safe being that it's a non-toxic, non-hazardous battery, cobalt-free, meaning lack of thermal runaway, so the ability to not go into thermal runaway, basically. UL certified 1642 on the cells, 1973 on the battery itself, and 9540A with some of our all-in-one components. And UN dot certified as well, 9480 and 38.3. Something also to consider, we SGIP approved. So if you're in California, looking forward to taking care of some of that, some of the money that you might have spent on it, and you want to apply for the SGIP program, definitely we are SGIP approved. So check it out and contact us if you have any questions about applying for the SGIP. Proven technology, over a decade of experience and growth. We've been in business for a while now doing this, building out batteries, deployed in over 40 countries, over 100 megawatt hours installed worldwide, tested and validated by the US Army and Marine Corps, and actually manufactured in the United States, here in California, actually. Simple, we always try to keep our batteries as simple as possible, maximizing any generation source, whether that is wind, solar, some sort of AC source, generator grid. We really are versatile in that sense and try to keep the batteries and the integration as simple as possible. Okay, for any of those that maybe have not taken one of my basic trainings and want to hear more about our batteries in general, definitely check out what's coming up. But for this presentation, it's a little more specified and specific as far as what we're going to be talking about. So really all I'm going to say about our batteries is what I just mentioned, and that we are a lithium iron phosphate battery company. That is what we use as far as our lithium chemistry with a cylindrical form factor. That is the basis of all of our products. Okay, let's get into the kind of meat of the presentation here. So again, we're going to be going through DC and AC coupling. I'm going to kind of try to stick to, what is DC, what is AC coupling? Why does one make sense in certain situations over the other? So what are some of the stigmas around kind of, I guess, misunderstandings, I think, a lot of the time around these, and a few other items. So basic definition wise, super easy. If we're looking at both AC and DC coupling as definitions, first of all, we look at coupling. So, I pulled this straight off the internet. Coupling, how solar panels are coupled to a battery relative to its charging. That's kind of typically what I would say. You could argue that there's probably, we're talking about coupling and there could be different, I guess, definitions outside of solar. We're just going to be talking about solar for the sake of the presentation. AC coupling, so coupling AC power from the inverter PV array to be converted into DC to charge the battery. That's AC coupling. DC coupling, coupling DC power straight from that PV array. It's already producing DC, and with charging regulations in order to charge a battery bank before it's being inverted to AC power. So a little bit more direct. Okay, so back to DC coupling. So again, what are we really talking about when we're talking about DC coupling? We're talking about DC power from generation. In this case, we're really talking about PV to the batteries. And there's no DC to AC to DC in this case. We're just taking that power from the solar array and going to the battery. But there is some things that happen in between. We use a charge controller. So, you know, what we're doing with the charge controller is we're controlling the DC power voltage in amps for charging the batteries. So, you know, if we have, and I'll kind of save this because this is more of a broad definition. The next slide, we're going to go into a little bit more. Some things to consider when going DC coupled, some PV considerations. We'll talk a lot about that later. There are some arrangements as far as string sizing and things that can kind of need to be put into consideration at the very least when going DC coupled versus AC coupled. But we're still supplying that AC from the inverter. We're just not inverting from the panels right away. Okay, so what does a charge controller do? It's in line between the solar and the batteries, but what is it really doing? Well, kind of broad definition, we're regulating DC voltage and current going into the battery bank to hit specific set points and battery limitations for charging from DC source. So let me explain that a little bit more general. So, you know, think about, you know, you've got your string, let's say we've got 3 panels strung in series, and we need, you know, maybe let's say our VOC is like 39, let's say it's 40 volts, just even. Obviously, you might not hit that VOC, but so just for our general sake, 120 volts on a string. You know, the batteries themselves probably want to be charged. I know our batteries specifically about 56 if we're talking 48 volts. So how do we get that down from that string size, from that string voltage to the batteries? So the charge controller can actually allow us to lower that voltage, which in turn will put the current a little bit higher and actually set that voltage that we want the charge controller to work at. Same thing with setting current limits. It can actually say how much of that we want coming through based on the battery specifications. So charge controller wise, the main things I see it used for, and I'm sure there's more, is DC sources such as solar, wind, and even hydro. I see these charge controllers used for. So charge controller wise, there's really 2 main ones that we talk about a lot, and that would be the MPPT charge controller and the PWM. So we're talking maximum power point tracking versus pulse width modulation. So what is the difference? MPPT, and I apologize for any of our partner charge controllers that are going to tell me that they want to go way more in depth here and really kind of, I'm simplifying this, but I really am just for this presentation. The MPPT really just detects solar panel output voltage in real time. It's always tracking that so that it can actually charge the battery with max power. So it's more of a constant charge, definitely. Whereas I like to look at a PWM as a bit of an off and on situation. It needs to find, it modulates width of pulse under certain conditions, meaning you're gonna definitely see, and again, maybe somebody might dispute this, a lot more efficiency out of an MPPT, excuse me, charge controller versus the PWM. As far as lithium batteries go, you can really use either one. I mean, we definitely have PWMs that we use for our batteries, and that's not a problem. But if I had to make a recommendation, I typically would say probably MPPT is going to give you a little bit more out of that solar array and as far as charging that battery. So as far as a quick diagram, this is actually one of Schneider's diagrams, and I'm actually pulled out a little bit, so they actually had a little difference showing here, but I want to really represent exactly what happens here. You know, we have solar array to the charge controller, And before we even go to the inverter, we are landing, and this is actually even misleading itself. Let's say we're landing on the batteries, but we're not actually landing on the batteries in real systems. There would be a DC bus right here, and the batteries would be connected, and the inverter would be connected, and the charge controller. All three of those would be landing on that same common bus so that the flow of energy can go to the least resistance. So if your batteries are full, hopefully, you can go straight to that inverter as well as to the batteries to charge. I've seen some older systems where they do run straight from that charge controller to the batteries, out to the inverter. Then everything's passing through the batteries, and I wouldn't recommend that. A common bus bar where they all land and then the power splits between them, it's going to be a lot better of a situation. That being said, we're still DC all over here. And really the only point where we're in AC is when we're going to either our dedicated loads, our main loads, or the grid. So this is DC on this side, and now we're in AC. Okay, let's talk about AC coupling. So AC coupling, we're really talking about, as far as solar goes, AC power coming off of the roof. Or let's say if it's a ground mount, sorry, that's a bad statement, as there are tons of different types of array, but really at the array is what I would think of, or at least close to the array if you're using a string inverter. So we are actually inverting the solar panels before they even get to the battery. So this could be using micro or string inverters, really a PV inverter to generalize it. I mean, here you can see, we've got our Fronius here, that would be our PV inverter. And then the batteries are actually charged with the internal charger of the battery-based inverter. This charger actually converts AC to DC power to charge the battery. So in this picture here, Selectronic, probably not, if you're from the US, you might never have heard of Selectronic. If you're from Australia, you know about Selectronic, big inverter brand out there. But this is the battery-based inverter. It's actually taking that AC in from the array that's already come off these Fronius, and it is charging the battery through its internal charger before inverting back out to AC power. PV considerations, I think, are probably one of the biggest things people consider when going AC coupled. If your array is already in place, it's going to make a lot of sense to go ahead and just use an AC coupled scenario. You don't have to rewire everything. You can just put that battery-based inverter in line. Bigger string sizes definitely is a big one too. That's changing a little bit. We are seeing higher charge controller voltages, like the Schneider 600 volt charge controller, which has actually been out for a while. But even the new Solarc stuff is a little bit higher in voltage, and the Outback also has a higher voltage charge controller. So they're trying to mitigate those smaller string factors, but definitely as far as AC coupled goes, you're always going to have larger strings, which is a win when it comes to system design. And you're still supplying AC from the inverter to power these loads. The only difference might be, my chart is out of place here. Let me just see how far away it is. I'm going to go jump here, and then we're going to jump back actually. Because I just want to make a point regarding the power flow here. So we do have the PV array here. This would be your grid-tied PV inverter. So maybe your Fronius in the case of that picture. And it is actually inverting right there, and it's going straight to that dedicated loads panel. So it's powering those loads as it sees them because it's already in AC. Now what passes through that goes into the inverter, and the inverter charges the battery as it's an inverter charger, and then it actually can invert back out to AC to cover the critical loads and to also cover the main loads or sell to the grid. So when the power goes out, this would disconnect, and this again is a bidirectional port here. So not only can we bring the PV inverter back online to say, hey, we're acting like there's grid here, we're frequency shifting, which we'll talk about in a second here. Please function again is the best way to put it. Please go ahead and turn back on and let that solar charge the battery, as well as be able to invert that battery power out to the loads here. So really cool systems. All right, to jump back. So battery-based inverters, chargers, and AC coupling. So again, this is the mechanism at which we would charge the battery. Instead of a charge controller, we're using the charger that's built into that inverter. So it's similar to a charge controller as far as how it acts on the output side, I should say. So, you know, we set bulk, we set absorb, we set whatever setting you want, and it still charges very similar in algorithm-wise as the charge controller. It's just typically taking in an AC source, which is actually a little bit more constant oftentimes than the PV that we might see on a charge controller. However, when we're talking about AC coupling, it still is technically PV that it's taking in. It's just taking it in from the grid-tied solar array, well, I should say grid-tied inverter that's already pushing out as AC from the PV array. Source must be AC in this case. As far as all the inverters I know, their chargers are built to take in AC and convert to DC. I don't know much that can take in DC and actually put out DC, or AC for that case. SolarArc's have been an interesting one here in this picture. They actually have a charge controller built in and that inverter charger built in. So you could go AC or DC coupled with either option, as long as you have the SolarArc. Programming wise, as far as charging set points, if it's coming from the grid, we typically tell you to charge at a little bit of a lower voltage because it's a bit more constant. We don't need to, you know, pump up the batteries as fast. When it's AC coupling, I cannot stress this enough. I think actually we'll talk about it a little bit later. It needs to be the higher voltage. So if you're looking at our 48-volt batteries, 56 volts is where I would always suggest bulk and absorb to be on a charge controller. And again, well, I think I do have some slides here coming up that will go over this, but you always want to make sure that 56 volts is set when you are, as far as the absorb and the bulk, and absorb time as low as 6 minutes. That's always what you want to use when AC coupling. It will work that frequency shifting a lot better, and that ramp rate will actually occur a little bit smoother. Oh, one more thing, using a generator efficiently during AC coupling. Careful with the generator. We definitely, for AC coupled, a lot of them require extra relays, extra hardware, so that you don't backfeed into the solar array. Just a consideration to keep in mind. Okay, so frequency shifting. What is frequency shifting? I've mentioned it a few times. This is the mechanic that we would rely upon to basically work with the solar array that's grid tied, that's AC coupled, in order to charge the battery, keep the solar running. Basically, a frequency shifting is let's just read right off this, is a mechanism used in a battery-based inverter to regulate or control a grid-tied PV inverter's output by actually controlling the AC frequency to regulate the charge. You might see some different styles where people aren't using frequency shifting, though it's very much the standard now. But blackout relays, you know, a bit of an on and off situation, kind of similar to PWMs as far as charge controller goes. You might see that sometimes, but frequency shifting, you know, actually changing that hertz signal and manipulating the PV inverters to output a certain amount. It's a bit of a tricky science, but it's getting better and better as these battery-based inverters are kind of refining how it works. Some considerations, especially when you're AC coupling, when it comes to frequency shifting. How old is your microinverter? How old is your string inverter? What is its frequency range? I was just told the other day, you know, if it's not Rule 21 compliant or can't be updated to be Rule 21 compliant and hit that right frequency range, probably don't use that grid tied inverter to AC couple. Maybe replace those. So, you know, I've seen things like the end phase 250s. I've seen them work. It takes a little bit of firmware updating and things like that. However, you know, if you've got the newest like the IQ8s on Enphase, those will work AC coupling pretty easily. That being said, easiest way to solve this problem and make sure that your system is going to work when you are adding a battery AC coupled, just call the inverter company, call the battery-based inverter company, or more importantly, call that grid-tied inverter company. Call Enphase, call Fronius, say, hey, this is what I'm trying to accomplish. This is the equipment I have. And they'll know. I mean, they've probably dealt with it a million times already of calls coming in, so they should know if that inverter has the correct frequency range to accept the correct frequency shifting and charge properly. Always check though. There's not just a list running of, hey, this inverter works with this. It's a bit more complicated. Okay. Let's talk a little bit about applications now and how applications relate to AC and DC coupling. DC coupling wise applications, and this is just some of them I'm listing off. Of course, there's tons more. The big ones I like to think of, off-grid being the biggest DC couple advantage. I mean, I will talk about it on the next slide, but DC coupling is the way to go if you're off-grid, 100%. And when you're off-grid and you're DC coupling, we can really use that float charge, which we don't necessarily recommend when it comes to AC coupling or when we have an AC source charging for the most part. But in a DC situation with charge controllers, use that float charge away. Battery backup, still we can, I think there's a big stigma around DC coupling is that it can't be, that it's off-grid only almost. Of course it can be grid tied. It can still do the same functions, that grid down situation with islanding mode. It actually has more functionality as a grid tied system than an AC coupled array would. So it's a hybrid system and it can actually utilize features like time of use, peak load shaving, and those various features, self-consumption. And if the grid goes down, it's seamless. The charge controllers don't even notice. They don't even blink an eye that the grid went down. The inverter will disconnect from the grid and the charge controllers are still just charging your battery. So I actually think DC coupling in a backup situation is actually kind of the way to go. Large scale CNI, I do still use, I mean, I definitely see DC being an option there. You know, DC to DC converters on a large scale. Medium scale built-in MPPTs you might see on these larger inverters like the Dynapower, the Princeton Power, or Ideal Power, those big ones. We got a lot of powers in the name there, sorry. But no, those are definitely ones you might see a really large MPPT built into the system. So a charge controller. PV considerations are a big one when it comes to large scale CNI is oftentimes you need to consider efficiency. Do you need DC optimizers? Are you running big strings without optimization on them? Various things like that. Applications AC coupling wise, I just mentioned off grid though for DC coupling. Do not go off grid for AC coupling unless it's on a large scale. So if it's like a commercial project, yeah, I get that. If it's a big microgrid, you might have a big bad inverter that can really mimic the grid. But if you're just a residence, you do not want to go off grid AC coupling. I've seen it done before and it's a mess. It just doesn't work properly. It's really not what it's designed for. Battery backup is the biggest use case I see as far as AC coupling. A grid tied array that's already there. I'm talking retrofit. Grid tied array that's already there. You're adding in a battery system in line. So that when the grid goes down, you can power your loads and you can also disconnect from the grid, but also bring that PV back online and charge those batteries. So if you've got sun and batteries for 4 or 5 days, you're still going. There are some limitations as far as the use case. So to go back, I mentioned, here we have TOU, peak load shaving, all those features we can use while DC coupling grid tied. Those are not, for the most part, there's a few exceptions. TOU and self-consumption and peak load shaving do not work properly when it comes to AC coupling. Especially time of use, which is it's a huge application. I see it a lot in California and people AC couple a lot. Time of use is just not going to work the way you want it to work. You can use grid timers often where it cuts in and out of the grid. But as far as true time of use, That's going to be a lot better accomplished when you have a DC coupled hybrid system. Okay. So retrofit versus new system, I've already kind of hammered away at the idea of, I'm sure you can kind of get my census on where I stand. So existing PV and AC coupling. If there's already a grid tied array and you don't necessarily need time of use and all these different things, you know, it's pretty easy to just add a battery AC couple. That's a good idea to just go ahead. If the grid tied array is already there, AC coupling definitely makes sense. Know your limitations, but makes a lot of sense. DC coupling at that point would be tough. You'd have to rewire a lot of stuff, add in charge controllers, take a lot of rework on the PV array itself. And again, as I mentioned, that island mode, when you are AC coupled and you're adding to an existing PV array, no longer do you have a customer that's saying, hey, my power goes out, my array goes out. Now it's my power goes out, my array comes back on. I've already talked about the misconception of DC coupling in grid tied systems, so I won't drive that home too much, but I think it also really comes from that retrofit challenges. So if there's a PV array already there, yes, you would not want to add a DC coupled system. But if you're starting from scratch, I'd say go DC coupled. It's going to make a lot of sense. It's really easy to accomplish too. Okay, rapid shutdown. Now let's talk very, very briefly about rapid shutdown, which this might even need a little bit of an adjustment on my own side here, these slides. But let's just talk about it. And I would like to emphasize, as I always do with anything code related, it's up to your local jurisdiction. I could tell you a million times how I interpret certain code or which code I think you're probably in, but in the end, your local jurisdiction is going to make the call on what is and what isn't. So they are the voice of reason on that one. You can argue, but they're the ones making the calls. So never take anything I say as literal, as it might change from code to code. DC coupled, though, we're often talking about, like, let's say a ground mount array that's off grid. I've seen those get away with, even in 2017 NEC, just shut off boxes going into the home from the array. That's it. No module level shutdown, even in that case. They just allowed for that shut off box. If you do need module level shutdown, DC optimizers oftentimes will have them built in if you go with the right ones. And really those RS only PV attachments like the Tygo and the Midnight, you can attach those to the panel. They're really affordable actually. And now your DC coupled system is indeed rapid shutdown compliant, just need a disconnect. So I've been kind of fuddling around with this. Mostly you can get away with the main PV disconnect, just being labeled properly. Now, if they need battery disconnect on AC or DC coupled system, just let me know. We'll contact us and we'll talk it through it. But the code technically says 2017 NEC, we don't need that. But I do see a lot of interpretations lately that we do need that. So there's some remote trip breakers we have options for. If you're using SolarArc, they actually have it built in where the inverter can shut down and act as the PV or the battery disconnect. But that is kind of a consideration that's going to be coming up a lot more as far as RSS compliance. AC coupled wise, microinverters and modular level shutdown, it's already there. You know, if you have string inverter, you probably have modular level shutdown too built in. If you don't, again, there's always options. Adding a battery in line just typically does not change your RS compliance, that rapid shutdown compliance. The modular level stuff's still there. Again, though, if they need battery level shutdown, there are some options that are pretty easy. Okay, we're kind of picking up some steam here. We've got just about 11 slides left. It might pick up here. Some of the last slides are a little quicker. System design consideration. So why would you go DC? Why would you go AC coupled? And I guess that more falls back to this category of application. But when you've decided, there still are some system considerations that you need to keep in mind as far as design goes. So PV sizing and strings. DC coupled. we're limiting amps through the charge controller, but we have smaller strings typically. Depending on the charge controller, you might get away with some of these new charge controllers that can do larger strings. They're probably still smaller than what you're going to see in a string tied inverter or running a bunch of micros in series. So you're oftentimes using combiner boxes and running those strings into a combiner and then running out. If you're using like the old, the 150 volt charge controllers, which are still really popular and they're still really useful, you're probably talking about strings of 3 on these new panels, which sounds daunting until you kind of get into the design and running into the combiner box, and it can actually be okay, but it's a consideration nonetheless. A lot more wire runs that way. As far as AC goes, and the AC coupling and string size, I mean, it makes sense. You're really able to string a lot more together, and have these large strings on the PV side. And if it's already there, it's already there. Retrofit's going to be a lot easier just going AC coupled. Less wiring that way for sure. Now, I will say one thing, and I hope I have this. I think I have got this coming up, so I'll harp on it once, and I'll probably have to harp on it again. As far as limiting amps through the inverter's internal charger, we don't necessarily trust it right now. So if you've got a solar array that's too big for your battery bank, we do not recommend tying that together. Actually, I know we've got a little bit on that coming up, so we'll hold a little bit. System design considerations as far as CNI goes, large PV systems, we're using a lot of optimizers, and we might require a lot of RS compliance, so maybe adding a lot of those little RS compliant attachments to the strings when we're using DC to DC equipment. AC coupled wise, that RS is probably already there if you're using, some bigger inverters. This Sunny Boy, whatever, it's not Sunny Boy, sorry, SMA, Tri-Power, those kind of ones like that. You're probably good to go. And you're definitely running a lot larger strings, which can be super helpful on a CNI scale where you need really big arrays and can run a lot more efficiently. Okay. So PV, or let's just talk a little bit about 5 products that we offer as far as AC coupling goes. Our standard batteries, and I'm going to get in trouble with this one didn't seem to make the update here, but the 2.9 is actually no longer, we're not manufacturing that anymore. So just that 3.8 standard battery, that is, our batteries as in general can handle AC coupling. They don't really care if it's DC or if it's AC going in, whether that's our standard battery or our new SimpliPhi battery with closed loop communications. These are really just, they're DC products. As long as that charger is correct, though, they don't care if it's AC or DC coupled coming in because it's still coming as DC. So it's still DC charging. Something to consider if you're AC coupled, you're going AC to DC to AC. If you're DC coupled, DC straight into the battery, AC out. I would always recommend 48 volt batteries if you're going AC coupled. The battery based inverters that work with AC coupling are almost always 48 volts. Our access solution, our all-in-one, pre-wired, pre-programmed solution is available typically in both AC and DC coupled. The Schneider is optional, so you have to add the charge controller as an option to go DC coupled. The Solar comes with both the charge controller built in and the ability to AC couple right out of the box. These are both higher voltage charge controllers, which makes string sizing a little bit easier. I mentioned this already, but grid tied compatibility, you can call us all day and say, hey, I've got these Enphase, M250s. Will they work with your Solar access? I'll probably tell you to call Enphase all the same, or we can call them together, but we want to just always check with the grid type inverter manufacturer. It's important to note if you're ordering the AC versus DC coupled access, when it comes to the Schneider, you have to say, talk to your distributors, make sure you specify which one you want, or you might end up with a charge controller that is not being used and programming that's not set up correctly. Okay, sizing considerations, PV to the battery. This one's super important to me. I mentioned this a little bit earlier, I'll mention it again. Your PV to battery needs to match that C/2 rate. So our batteries can handle C/2, meaning, you know, if we've got a 3.8 kilowatt hour battery, we can handle 1.9 kilowatts per battery. So basically just take your entire battery bank size. So say you've got a 14 kilowatt hour battery bank, divide it by 2. The max PV array would be 7 kilowatts. And we can set that charger to limit the array, but when it's AC coupled, we really need to kind of keep that limit in mind, because it can, frequency shifting is not a perfect science just yet, and it can mess up. Access energy storage system, as far as ATS goes, automatic transfer switch is built into all of our access, so that island mode happens automatically. Just need to make sure you got a critical loads panel put in. They're outdoor rated, which is great for AC coupling. Most of your equipment's already outside, so it makes a lot of sense to add in something that's also outdoors. Okay, I mentioned the PV limits. We just make it super obvious when it comes to our access solution. What is the PV limits when you are AC coupling? There it is, right there. The Schneider 3 battery is 5.7. The Schneider 4 battery is 6.8. And the Schneider, or the Solarc 12K model is 7.6. This is either typically based on the battery's max charge rate or the inverter's max AC coupled rate. Whichever one's lower, we will take. But these are super important to keep in mind. Don't AC couple us, you know, as 10 kilowatt hour array, or sorry, excuse me, kilowatt array to a Schneider access 4 battery, or you are going to fry the components in the inverter and maybe even fry the battery. So keep those. Those are actually in the manual, section 3.1.1. You can find this list of limits AC coupled. It's also on the spec sheet, I believe, too. All right, just to kind of wrap things up a bit regarding design tools and help. First and foremost, if you're looking for some design tools and some help and a little bit of an overview of the website, next week, my webinar on our web tools, and we're going to do a little tour of the website. I'm going to go through all sorts of things. I'm going to walk through where to find the correct manuals, spec sheets, integration guides, which really are super key. As far as AC DC coupling too, we talk a lot about that in there, and it gives the exact set points. So please, if you're interested in that, attend. We're actually going to be talking through these various tools as well. Battery sizing tool we have live, the system battery sizing tool, which is a little bit more in depth, lead acid replacement tool. We're even going to go over things like levelized cost of energy storage and various tools there too. If you do have any questions about stuff I've gone over, my email will be right at the end here, but you can always call our support or our pre-sales line. Good news is our pre-sales line is actually not just a bunch of salespeople, it's application engineers that can help with design if you are starting out. If you've already got the system and need some help, call the tech support line as well. You know, we're available 5 days a week, and we will pick up, or at least make sure that if that line's busy, we'll call you right back. Okay, last little thing I want to mention here. If you don't know about our installer qualification program, this program is not a requirement to install our batteries. It's more of an added benefit for people that are installing our batteries. Well, let's see if it works here. Oh, that is unfortunate. I can't seem to go to that link right now, but basically this is a program where we highlight those that have installed some of our batteries. The requirements are install 2 batteries, you know, pass a very brief quiz regarding our products, and show us a few pictures and things like that. You get a nice little spot on our where to buy page, showing you not as somebody that technically, you know, is a distributor or anything, but you are you are somebody that we trust to put enough on our website that homeowners will call you and say, hey, I want a system installed. I saw you were on the where to buy page of SimpliPhi Power. Really cool program. Again, not a requirement to install our batteries. You actually need 2 installs to do it. But if you're interested, go to the website, go under support, I believe, and it's going to be under SimpliPhi IQ installer qualification program. Scroll down and there's actually an application you can fill out. Takes 5 minutes, not even, and just send it over to us, and we're happy to look through, work with you, and get that installer qualification logo there, as well as get you part of the website. So really cool program. We're actually going to be talking a lot about it next week as well during that presentation. So if you're interested, shoot me an email or jump on that presentation next week. Okay, I lied. My email is not here. Let me just go ahead and add that in for everybody, because I do want everybody to have it. So there is, whoops, all right, 1 second. There's my email address. So if you have any questions regarding today's material that I don't cover off these Q&As, again, if you've got Q&A questions, you can type them in right now. We've got some time. We can go over these questions, but if there's anything I don't cover or if something pops up afterwards, you can always shoot me an email there at training@simpliphipower.com. Or if you're curious about the IQ program, can't find the application or anything, shoot me an email there too. First question is, how do I get a copy of this presentation to help with customer sales? Yeah, we'll actually send it out automatically with the recording as well. Takes us just a moment to get on our YouTube channel and send out the links. We will send a follow-up with that. When you are charging in the basement, as in your picture, let's look at the picture here. Let's find the basement picture. I'm guessing this is what you're considering the basement. Not a basement actually, but doesn't matter. There's actually a barn, I believe. Do you need ventilation for fumes? No, our batteries do not off gas, do not require ventilation. I've seen them in tight little boxes together, being jostled around, no ventilation requirements whatsoever. Using a 600-volt charge controller like the Morningstar and Schneider make replacing an existing grid-tied string inverter not too bad. Obviously doesn't work with microinverters or solar edge. Amy, that's a really awesome point. I think she's going back to talking about considerations when you're retrofitting. You know, if you do have a string inverter that you want to replace and go DC coupled, these larger 600-volt charge controllers, and Morningstar, thank you for mentioning that one. It's one of my favorites. That's a really awesome new product they have, that 600-volt charge controller. We can add in that charge controller, replace the string inverter, and go DC coupled on a grid-tied system, even if it is a retrofit. Are there any requirements for fire or fire alarm systems? Well, fire, as far as rapid shutdown, we kind of already talked about. As far as fire, I mean, basic electrical code, you know, I think the electrical code still calls out maybe a fire extinguisher or something along those lines. If it is commercial project, there are further requirements. I don't know them off the top of my head, but the good news is our batteries don't have that chance of thermal runaway, so we don't have any sort of coolant systems or anything like that. Do you have any products in Africa, like Nigeria, support in Africa? I mean, yeah, shoot me an email. Let me go back to my email here so everyone can see it. If you are interested, either shoot me an email or shoot our sales email, sales@simpliphipower.com. We actually have a rep that specifically kind of works in the Africa market and can help out with distributors and whatever support you may need. Awesome. Well, I don't see any other questions coming in, but I just want to say a big thank you. Okay, one more. What are the range of costs for batteries nowadays? I'm not on the sales side. I don't try to mess around with what the cost is. You can see some MSRPs if you look around, but it really does vary depending on who you are. And I know you're asking roughly, what is it? I can't really give it. It's just, it's so varied. I mean, I'll tell you what I see down the street. MSRP might be $3,000 for a 3.8 kilowatt hour battery of ours. It's probably a lot less if you're a distributor. Definitely a lot less, even if you're a homeowner. It's probably less. But that's just kind of that standard number. I am building a small 600 watt portable AC power systems. Need to be 12 volt, probably Morningstar charge controller. I'm concerned about not having enough current to charge at C/2. What is this? What is the smallest battery? 1.4 is the smallest battery. If you need to charge faster than C/2, let us know. We do have some products that are rated for greater than C/2. They are high output batteries. All right. Well, hey, everybody, again, I really do appreciate everyone's time. We'll shoot out some follow-up with the recording and whatnot. And we will try to really kind of answer any questions that you may have. Or if you want to shoot us back an email at training@simpliphipower.com, we are happy to help there as well. Awesome. Well, I really appreciate everybody's time, and thank you so much.